I know. But it won't matter right now. And it wasn't bad. It's always I'm not artistic. I can do music. My one friend's like, I was able to have one friend go, oh, draw a soul shaker. I was like, Evan, you know I can't do that. Like, you know I cannot do it. Yeah, he's like, draw this soul shaker. I was like, I can't do it. Draw this light. It's like, I can't do it.
I'm not saying I did it.
Yeah.
Or
Yeah. September's almost over. I'm not happy.
Yes, so please take 2 of these. So 2 of those, good. 2. And 1 of these.
I'm emotional, yes. I'm very sensitive and very emotional.
Hello, Zach. If you're just coming in, we've got 1 of these and any 2 of these. Right? They can be the same, they can be different, doesn't really matter, but we need 2 of them. How are you, Jess?
Good, how are you?
All right, thank you.
I always forget to get there. You all
Okay, we've got 12:30, so why don't we get started? Good afternoon, S&P. That's a terrific response. Congratulations to all of you on a really wonderful Exam 1. I've been doing this for 15 years. This was far and away the highest performing Exam 1 that I've ever had. So I'm not sure what that's all about. It might be that TED Ed is working for us. It might be that I just need to make Exam 2 that much harder. But I've never had an Exam 1 anything like this. Most people did extremely well. A couple of people struggled just a little bit, but generally speaking, people did really, really well. So maybe, at least what I'd like to think, is that TED Ed gives us an opportunity to ramp up rather than take a steep step. So hopefully that's working for us. So congratulations on a job well done. Okay, so just before we get into today's topics, I want to make sure that we're all on board for what's due on Wednesday. We'll have another TED Ed. Now we're starting in earnest into the eye and the stimulus for the eye. So we were talking about the human eye part 1, and that actually had a part 1A and 1B, as you'll recall. And then we have some more about the human eye for Wednesday's TED Ed. Okay? There's a chance that we will be visited on Friday by a recent graduate of this class. Her name is Rachel Fenton. Some of you might know Rachel. She's now in optometry school just down the road. We have another Rachel, whose name is Rachel Reed, and Rachel is also in optometry school starting this semester at the University of Houston. And I'm going to try to have her Skype in at some point. But Rachel Fenton might be joining us on Friday to talk about the human eye and what it's like to be in optometry school. So it should be an interesting week. Okay, so with that, let me begin by opening up to see if we have any questions about general comments on the TED Ed for today. Excuse me, before we start talking about particular questions. Okay, let's do a wave. Let's do the wave. Put our hands out like this. Okay, and let's do it this way. Let's go up and then down. Excuse me, I'm going to grab some water. I don't know, I'm dying here. Pardon me. Okay, thanks for bearing with me. I think I'm back among the living. Let's do the transverse wave, and we'll go up and down. So I'm going to point to you. And as I go this way, you'll raise your hands up, and then when I come this up and down, and when I come this way, you'll do it again. Okay? So here we go, starting on this side. All right, and we'll come back. Okay, well, stay with me. Stay with me. Try not to get ahead of me. Okay. Now, why is that a transverse wave? That's really good. Okay, this group is extraordinary. Why is that a transverse wave? Jess has it. Okay.
Because you're moving like perpendicular to the wave moving this way forever.
Okay, really good. She's also, for those of you who can't see her, she's moving her arms appropriately. There's a perpendicular relationship between the local motion and the overall traveling disturbance. We can think of a wave as a traveling disturbance, and so we have now some local motion that is perpendicular. What type of environmental energy moves according to a transverse wave? Can you all yell it out? Okay, light, right? So we're going to be talking about a different kind of energy in a few weeks. It'll probably be 5 or 6 weeks before we get to talking about acoustic energy, which will move in accordance with a longitudinal wave. Okay, so let's make sure that we're all okay with that. So this time, I will ask you to stick your arms out like this. And this one's harder to do. You've not seen this one before, probably. So can you stick your arms out just like this? And we're going to do something a little bit similar, but when I point to you, I want you to pretend that you're hitting your neighbor on this side. You don't actually have to make contact, but you're going to swing into your neighbor. Your neighbor will swing into his or her neighbor and into their neighbor, almost like a domino effect, okay? And then when I get all the way over to Meg, we'll come back this way, and we'll see if we can do this a little bit harder, okay? So here we go with the longitudinal wave. And stay right in position, and then right back this way. And then let's do it a couple of times, a couple of cycles. Okay, wait to get hit. Wait to get hit, right? And one more. Okay. All right. Okay, so I think we get it, right? In each case, we have a left to right traveling disturbance. One is the parallel case, which is longitudinal, and that's the way that air molecules work, as you're hearing my voice. And my voice, by the way, is coming to your psychological experience by way of your 8th cranial nerve, whereas the transverse wave that is light is coming to your psychological experience by way of your 2nd cranial nerve. Okay, so we have different kinds of waves coming your way. Okay. By the way, I want to make sure that we come back to this in a few weeks, but we'll just do that one more time. We'll do the longitudinal wave, and I'm going to freeze it and make a point about a particular pair of air molecules, if you will. So can we do that one more time by sticking our arms out? Okay, and we'll get going like this. Okay, and we'll get going like this. And can we freeze right there? So just a moment ago, right here, okay? So Claire and Melanie, these molecules are very close to each other, but in a moment they're going to bounce, and then they're going to go their separate ways, and now they're very far apart. So we can talk about how many molecules do we have in a small unit of space versus the same number of molecules in a bigger region of space. This is tightly packed, this is sparsely packed. And we're going to be talking about how you're hearing my voice by having these compressions and rarefactions of air, tighter or more loosely packed air molecules that give rise to the sound. But we don't have to do that just yet. We'll come back to that idea in several weeks when we talk about measuring the physics of sound. Okay? All right, so those were a couple of the opening ideas talking about light. Why don't we do this? I'm going to call up the PowerPoint, okay? And the first several of these, we had the facts of light. I hope you enjoyed the pun as much as I do. Okay. And we talked a little bit about different properties here and so forth. And maybe through the first 16 slides, that's really all we had in part 1A, the first 16 slides. So what I'll do is I'll just keep these up here. I'd like you to get with a partner and just sort of teach each other about these slides, and then I'll ask you, some of you, to walk us through some of these slides. Slides are kind of self-explanatory, and so I'll keep them projected up front here. But why don't you practice with a partner as if you're teaching your partner all about these first 16 slides. This is part 1A, okay? You can just teach each other informally, and then we'll see what you want to share about these slides, okay? So if you can find a partner, that'd be great. You can use the same partner as always, or find a new partner. You might need to be in a trio. If you see somebody who's left out, please bring them in. Okay, so teach each other about these first slides. This is rehearsal. And I'll keep going like this. Maybe that's better. Okay. Thank you for teaching each other. Okay, why don't we come back? Why don't we see what kinds of things we learned about, or we can also see what kinds of things remain confusing. Okay, so what kinds of things were new to us, and what kinds of things are clear, but what kinds of things are confusing. So anybody want to start us out with, well, I can point to something, and maybe you can say, you can speak around these slides. Okay? Wave-like and particle-like properties. We've already done some wave-like properties. Can somebody say a little something about particle-like properties? Try to do it without using your notes. What are the particles? Photons. Photons, okay, right, all right. How do they differ from each other? How might photons differ from each other? Okay, thanks.
So there are high energy photons
okay.
and low energy photons.
Okay, right.
And high energy photons are short wave?
Yeah, they have a shorter wave, okay.
And it has to do with like how long how far they can travel during the course of an oscillation.
Wow, okay, and for those of you who didn't see it, she made the oscillation for us, so we'll make an oscillation that goes something like this. And we'll do one cycle. We think of it as going up and down. Okay, that's the wavelength. Okay, right. So we have higher and lower energy. So I think in the PowerPoint we talk about high and lower energy. Actually, there's a continuum here, right? There's a continuous level of how high or low the energy is. And this is really the rate at which it's oscillating. I'm showing it here as going up and down. So these things are kind of moving. For those of us who have played some American baseball, you might know that as I throw the ball from me to Jess in the back, it's moving along this axis, but it would also be going maybe like this, okay? And it could be moving at a particular rate. It could go over a longer trajectory as it's making its oscillations, or a relatively shorter trajectory. It's always moving at a particular speed. What is the speed? Regardless of its wavelength, what is the speed of light? Yell out if you know it. 1 times 10 to the, that's an important number. 1 times 10 to the negative 9. Okay, that's what is that? 1 times 10 to the negative 9. Nanometers. Okay, right. Okay, so that's and that corresponds to what kind of a unit? Is it millions, thousandths? Billions with a B, okay? So billions of a B. And so we take that meter, divide it into billions, and that's the range over which we're talking. So one of these oscillations might be something like 400 nanometers or 700 nanometers, so forth, okay? And can we get now back to the speed at which we travel across space? Light travels, the photons travel at what speed generally? 3 times 10 to the 8th meters per second. 3 times 10 to the 8th meters per second. I apologize for that noise. If we close the windows, it gets a little bit warm in here. But so hopefully you can all hear. 3 times 10 to the 8th meters per second is the speed in meters. Anybody know what it is in miles? 186,000 miles per second. It's quite amazing, really, to think about that. 186,000 miles per second. The idea would be that a photon could wrap around planet Earth several times in 1 second, right? It's pretty fast. Even at the widest portion of Earth, it could move that quickly. All right, so those are some of the facts that we have about these photons. If I had a shorter wavelength photon, I might still go up and down, a complete iteration of a pattern, but I now do it over a shorter interval. So I'm going to mark this as my halfway point, and I want to go all the way up, down, and all the way back up in half the distance. So I might go something like this. Right, so we had something like this when we were talking about neural handshaking. Again, we were talking about frequencies, but they weren't frequencies on this small time scale. So we have these photons that are relatively higher or lower energy, and they have different psychological correlates. Okay? So can somebody tell us what we mean by the idea that the rays are not colored? That was another idea that came up here. The rays are not colored? Meg's got something.
The rays just like a wavelength representation, and then our psychological perception is what.
Okay, right. So all that's physically varying between these different kinds of photons is their wavelength, the duration of, or the length of space over which they're oscillating. Okay, and they can oscillate relatively quickly or relatively slowly, but they're always moving from one point to another at the same global rate, but they've got different oscillation rates, and that's just something about the physical property. And so can you show us by gesticulation the psychophysics graph? How do we graph psychophysics here? Okay, psychophysics, can we all do that? Let's do it in the air. Psychophysics, there we go. All right, so on the physics axis, we can talk about different wavelengths of light, and our range might be something like 400 to 700 nanometers. Okay, has anybody experimented with these night vision goggles that can pull in other kinds of frequencies for us? Maybe you've seen they can also operate at really, really low light levels. They send out beams of infrared light, and they have things bounce back, and the goggles translate that electromagnetic energy into the range that you and I can see. And so pretty cool. Pretty cool. How many people, has anybody used those before? Night vision goggles? Okay, they're kind of geeky, so I wouldn't expect that you would necessarily have some of those. Okay. All right, so we know now something about these different properties. We know something about the wavelength duration that we're working with, the speed at which this is moving, the range that we can see. We've got something now about the particle properties. Okay. Other questions? Yes, please.
So just to kind of clarify this, when we
Sure.
the length of the wavelengths determine what colors we see.
Yes, yeah. Isn't that weird? So I'm looking at Claudio's spectacular red shirt, right? But there's really nothing red about it. Physically, his red shirt will be something closer to the 700 nanometer wavelength portion of the spectrum, okay? So we can see between 400 and 700. And what's hitting me from his, and now he's got a red bottle. Oh, look at this guy. He's all red. Can you hold that up for all of us to see? That's glorious, okay? All right, okay. Now there's a good red stimulus out there. But actually, if Billy Wooten, my doctoral advisor, heard me talking about this, he said, no, the stimulus is not red. That's a stimulus error, right? We experience red. This is really long wave energy coming out here. So really, really intriguing that we have a very compelling sense of color, right? But there's nothing colored out there in the world, or nothing is. That background noise that we can hear, kind of distracting, but in a way it's good. It's got a certain pitch to it. Again, that pitch isn't really there. All there is a certain frequency of compressed air and rarefied air landing on your eardrum. We experience it as a particular pitch. We experience that wavelength as a particular color. And Tawny has a slightly less long wavelength coming out. It's almost a yellow coming out of her sweater, right? Okay, so interesting to think about what's physically out there. That's the x-axis in psychophysics, and what we psychologically experience. And of course, if we take this back now to our conversation on consciousness, Dr. Nick Lane, the biochemist, would tell us, well, it doesn't really matter whether we perceive the wavelengths or we perceive colors. We do need to be able to function. We need to be able to operate in our environments. Fundamentally, his bottom line was that consciousness was about life and death. Okay, so however you experience these different wavelengths psychologically, it doesn't really matter as long as they're functioning for you, right? If you can tell that that's the dangerous berry and that's the not so dangerous berry, right? Now that's adaptive. So it helps to make a wavelength discrimination. Whether a particular organism experiences that as a color or as a something else is kind of neither here nor there from an evolutionary perspective. But as psychologists, we're very interested in that y-axis and what's driving it on this x-axis. Okay. So I won't dial right down to it. Can we go over some of the F's associated with evolution? There are 4 F's of evolution. Anybody think of, can yell out one of them? Well, okay, let's come back to that F last. So before we come to that F, what was the fighting? Okay, sometimes you have to compete for space or for food, so there's fighting. Yep. Feeding, okay. So we have to, we're just talking about finding the appropriately colored berries and so forth. Honey's got something. Fleeing, sometimes you just have to get out of dodge, okay? And we need to be able to navigate our environments to do that. And of course, our last one starts with an F, and it is, we said it earlier, reproduction, right, okay? So you can imagine what that other F might be. We're all adults here, so I'll say it. Flirting, okay? You were probably all thinking of the other F, which is fooling around. They'll come to you all day long. It's amazing how many F's you can put in there. There's not just the one that he was alluding to. Okay, but that's another F, and this can be very important for us if we're thinking about picking out partners. Sometimes if you were color coding for potential mates is very important for birds. They're sometimes attracted to mates of particularly colored feathers or tails and so forth. So really important that animals are sensitive to the different colorations that arise from the wavelength differences. Okay, so why don't we end this little portion with just some of the different advantages for electromagnetic energy in general. If an organism is sensitive to that, why might that be advantageous? And then maybe the portion that we can see, 400 to 700 nanometers, why is that advantageous? Somebody want to help us with any of those advantages? Zach's got some.
Electromagnetic energy is very fast.
It's essentially, I mean, it isn't literally instantaneous, right? So it does take some finite amount of time for a photon to come from that light, hit your shirt, and hit my eye. But it's so fast that our nervous system really can't discriminate, right? That latency. So it's essentially immediate. So you get really fast information. And if I can pick up on that just for a moment, one of my favorite factoids is, if you've probably seen these videos on neural control, they'll put an implant in a person or in an animal, and that animal can think about moving its arm. Right? Its arm might be stationary, and it can actually move a robotic arm. Ever seen this? It's really cool. You can keep your hand stationary, and you can move a robotic arm just by thinking about it. And the way that works is that there are implants that are basically picking up patterns of neural activity that you would have been using to move your arm. And that pattern is being read by some kind of a sensor, and it sends a signal out to something like your garage door opener, right? That moves an arm that opens your garage door. Has anybody seen the Star Wars game where you've got these cold electrodes on your head, and you think about moving this ping pong ball up through a tube, and there's a small fan down here. And once your brain waves get into a certain state, it sends out a signal to this fan, and it drives the fan, and now you're sort of operating that ping pong ball, making it go up and down just by thinking about it. Has anybody seen that one? Okay, and thank you for not being embarrassed about showing off your geekiness. We had one student a couple years back who brought that into class, and we took turns using our mind to make this ball go up and down, which is pretty interesting. So what I think is really interesting is that you can do this with a monkey, and they did this recently in 2 different laboratories. One was in Duke University, which is in Durham, North Carolina. And then the robotic arm that was being moved was in Japan. So the animal was sitting in North Carolina thinking about moving its arm, and it would occasionally move its arm, and that would also then generate a moving arm over in Japan. What's really cool is a signal could go faster from using EM, can go faster from Durham, North Carolina to Tokyo, Japan. Then the signal can go from my occipital lobe down my arm. Right? So if you think about how long it takes to send a action potential from here right on down to here, it actually takes longer than it takes for a photon to move from here or the United States somewhere to Tokyo. Okay? So isn't that pretty cool? That's how fast that is. So yes, it's advantageous to have that fast information. A couple of other advantages associated with either EM generally or light specifically. Madison has something. Yeah, it moves in straight lines, and that preserves shape information. So now we get shape about potential food, shape about potential enemies from whom we have to flee, shape about potential mates. Okay, we get shape information, and we get it speedily. So that's really a tremendous advantage. As we'll see when we contrast electromagnetic energy with acoustic energy bounces around and it wraps around things, and light doesn't do that. So I can hear you around the corner, but I can't see you around the corner. Okay? That's just a difference in the property of those 2 different kinds of energies. So we get shape information. Some other advantages associated with EM or light specifically. What was the? Yeah. Okay. Go ahead, Madison.
You said that it bends.
The acoustic energy bends, right?
So how we use a prism to bend light?
Okay, you can refract light, right? So generally speaking, light will travel in straight lines until it's going to hit something that's going to bend it. But then even after it gets bent, it will travel in straight lines from there. Yeah. Yes, thanks.
Light specifically that we can see is it bounces off of objects.
Right.
So it doesn't travel through them, so it lets us know where they are.
Right, so not all light is quite as bouncy or reflective as our particular range of wavelengths is, right? So you might remember that a microwave oven also uses EM, but that's actually sending light waves through the food, right? It's not bouncing off of that. Okay? So it helps to bounce, and it's bouncing while preserving shape information and very quickly. Okay? Last one was that there's plenty of it, right? At least here for terrestrial animals, there's lots of light in that range, lots of EM in that range. So if you're sensitive to that, you can take advantage of it. There are some animals that are not. Bats are relatively insensitive to light, which is fascinating because their ancestors were considerably more sensitive to light than they are. And we'll have at least a whole day on bats later on. One of my favorite days of S&P is we talk about bat echolocation. For now, why don't we move on and why don't we begin to play a little bit with the filters that you've got. Before we do that, though, I wonder if somebody, maybe we can get 1 or 2 people to come up and draw on the board for us these luminance profiles. We have a luminance profile for a polarized lens, and I think one of the questions was to have you do that by draw to. Right, so you went to draw to, and you were drawing the luminance profiles for polarized lenses. Can we get a few folks to come on up and do that? Luminance profiles. Any volunteers? Claire, thanks. And Connie, thank you. Yeah. Maybe we can get 1 here and 1 over on that side. So we'll do the polarized lens, okay, as opposed to the smoked lens. And while they're doing that, why don't we first take out one of these, and we'll let them catch up with us in a moment. So does everybody have at least one of these? And they're slightly different. I have an older pair and a younger pair, but they hopefully all work the same way, okay? You can first put them on just to assure yourself that you do get some reduction in the total number of photons coming your way, which is to say that they're getting darker. Let's give Sarah, and we'll need two pairs, Sarah, so just put on one for now. Okay? All right, so people are hopefully getting some reduction. And if I've got my stimuli right, if I have these all correctly handed out, these are polarized lenses. We're going to contrast them with smoked lenses. Actually, I should call them filters, not lenses. These are polarized filters. Okay? Now, if you'll take your other one, I'll wear this just for a moment. And maybe you can cover one eye. I'm covering my left eye. I'm taking my right hand, and I've got a filter kind of like this. And you can put it over and then tilt it back and forth. And you might notice that as you tilt it around and you're rotating it around, there are certain angles that work really well in letting light pass through, and there are other angles where it gets really, really dark. We'll see how many people are having that experience. How many people have that? Okay. All right, pretty cool. Pretty cool. Right, so we're getting some idea about what's going on here with these polarized lenses. So over here, we're saying number of photons, and I think on some of my graphs, I have a ridiculously low number of photons. And it's difficult to imagine how many photons are floating around this room. I'm going to call it 100, if you'll bear with me. Okay, that's going to be sort of the maximum number of photons coming to a particular location. And then we can put on these polarized lenses, and your left and right eye polarized lenses have oppositely tuned filters. So it might be that essentially one of the two is blocking out, I'll call them vertical. It might be some other angle, but I'll say the vertical plane of polarization is being blocked, and very, very few photons are coming through. These filters, I think I got a stack of them for like $9, and we probably got 50 of them for $9. So these are really low end, right? Okay. So they don't block all of the light at that particular plane of polarization, but they block a lot of it, enough that you can clearly see that you're getting a reduction in light, and enough to make this demo true. So we didn't get all the way down to 0 photons, but we got down to most of them, and we're going to block a full range of degrees. We can think about this physical axis as corresponding to something like the degrees on a protractor, right? That would go from 0 to 180 degrees. We might say that this is hypothetically vertical. And then as you move over through more and more degrees toward a horizontal angle, we're getting an increase in the number of photons until it finally levels off. Okay? And then, of course, the other eye that you've got, the other filter, has the complementary set. Okay? So you're blocking out two different planes of polarization when you do this. Now, what's interesting is when I put them on, I get the sense that it's gotten darker. But I really can't tell you which one is which. Right? I can't just look at them like this and say, oh, this is the one that's blocking out this plane, and this is the one that's blocking out that plane. Let's see if you can corroborate that. Can you put on any one of your pairs, and you can tell that it's darker, but you can't really tell which one is which. If you just have one, we won't have the second one yet, Abby. Just that first one, right? Now you can't tell which way these things are angled, right? But as soon as you hold up this one, even from a distance, you can probably tell that one of those looks, if you close one eye, even from a distance, you can probably tell that one of those looks dark and one of those looks light, right? And if you tilt it, the one that looks dark or light, right? Yeah, if you switch eyes, it changes, okay? Okay, really good. So if you switch eyes, it changes, right? So close one eye and then close the other eye and keep this thing rotating and close one. So you can see that you have two different planes of polarization being blocked. Now, you and I can't tell that because we're lowly vertebrates. We're not really good at this. Actually, I'll say mammals. There are some vertebrates that are pretty good at this. Can somebody think of a vertebrate that probably could tell that plane of polarization? Is there a vertebrate that you can think of that might be sensitive to how light is polarized? Yeah, some kind of insects. Okay, insects certainly are going to do this. They're really good at that. Is there a vertebrate a little bit closer to us evolutionarily that can do this? I don't think I mentioned it in the video. I just wondered if any. Yeah. Actually, I'm not sure that cats. I'm not aware that they can do this. I think, well, cats are mammals, and I think that most mammals can't do this particularly well. Yeah.
Owl.
Owls, probably owls. I think a lot of birds can. So the idea is, how do birds figure out which way is south and which way is north when they're navigating? And the thinking is that they're actually sensitive to different planes of polarization, and that if you're getting light from the sun, you can almost look at it. You and I can't look at it, but a bird can, and they can look at almost how it's oriented, if you will. They basically get a clue, roughly like the clue that you and I get when we can play with these things like this, except they don't need goggles to do it, right? You and I need these. Their eyes pick up on that, and that helps them figure out what's the north-south plane. One of the pieces of evidence for this is they had birds in a large area, kind of like the Mitchell Center, and they were able to put light in of a particular plane of polarization and then systematically manipulate that plane of polarization and see if the birds would follow it. And the birds followed it pretty tightly. So the thinking is that here we have an animal that does have a backbone. It's a bird, and it's probably how birds navigate. There's also the African dung beetle that uses polarized light to sort of find straight lines up there in the stars and move its dung along a relatively straight line from an open field back to an area where it's a little bit more closed, and it can eat its dung without being harassed by other dung beetles or other kinds of predators. And you know, if you're in a hurry and you're trying to move your dung from here to here, the shortest distance between two lines, between 2 points, is a line, right? So we want to make sure that we're following a very straight line. And they're using polarized light to find straight lines to help them navigate how they're rolling their dung from point A to point B. So really clever. These animals have all kinds of clues available to them in their sensation and perception, which we don't have in our sensation and perception. Who's following that? Working for us? Okay. All right. Really, really good. Okay, so those are some ideas about polarized light. Okay, we've done all of this. Okay. Okay, let's talk a little bit now about a smoked filter. I think we have time to do a smoked filter. So how would this change for a smoked filter? How would this diagram change? Okay, thanks, Claire. Okay, so yeah, this one's going to come down a bit, this one's going to come up, and so rather than having all the photons coming through, we're going to block all planes equally. Okay, so the interesting thing about a filter is it allows certain photons to pass, other photons not to pass. This particular one is selective for different planes of polarization, but you could have just been, if you will, even Steven across all possible planes, right? And then, of course, how many people have gone to 3D movies and maybe you've got a red side and a blue side? Has anybody done that? Okay, so now maybe you can tell me, how are those operating? Those are also blocking certain photons, but how is that different from what you've got here? Okay, so these are blocking different planes of polarization. Okay, what are the red-blue ones doing? Any notions about that? Okay, thanks. Yeah.
Blocking certain photons.
They're blocking photons. Good. Okay, and and these are blocking. So here we're blocking these photons, right? Here we're letting these photons pass. In the smoked filter, we're blocking kind of all the photons equally across planes of polarization. We're going to block some photons in our red and blue goggles. Did you want to add to that, Liz?
Yeah, so I was thinking it was more along the lines of like the shorter wavelengths are like blue and higher rates of oscillations, right?
Yeah.
And then red is the other way around.
Yeah.
So there it's just the distance of the wavelengths.
Okay, really good. Right. So what we can do is we can still have a filter that's going to block some photons and let others pass through. But instead of having this axis be planes of polarization that ranges from a vertical orientation to a horizontal orientation, we can now have them block different wavelengths of light. Okay, regardless of how the wavelengths are coming to you, regardless of whether they're coming to you like this. This is sort of a vertical plane. Okay? This is a horizontal plane. This is one of the diagonals. Okay? But I'm moving my hand at about the same oscillation rate in all these cases. What I could do is keep my hand moving now at a much slower oscillation rate, longer wavelengths, but still in the vertical plane. So we can block them on the basis of wavelength, or we can block on the basis of a plane of polarization. Lots of different ways of blocking light. Who's following that? Is that working? Okay. And so what's cool about this is you can also see 3D movies using these kinds of filters. And the way that might be photographed is you would have two cameras that are taking a picture of this room right now. And in front of this camera, you might put this kind of a filter on the right side. And in front of this camera, you would put this kind of a filter. And you take sort of two shots of everything. Okay? And then when you project it out, you're having people watch it through this, so only like the vertical plane is going to make it into this eye, only the horizontal plane is going to make it into my other eye. And you get some really interesting 3D effects by doing that. We'll talk a lot about 3D vision. Okay. All right. I think I've got some smoked filters. Can we do this? Why don't we have you take one of these, and you only need one. Now these are a little bit different in a couple of ways. One of them is just a regular see-through. It doesn't do any filtering whatsoever. The other one is darkened. So if you'll take one, and you only need one. If you'll take one and pass, you'll take one and pass. One and pass. Yeah, you can put those on. Okay, these are called Polarized glasses, and one of my favorite demos will happen in November when we do the Polarized effect. We're not going to do the Polarized effect today, but we've got this, and it doesn't really matter whether your right eye is darkened or your left eye is darkened. I see we have a mixture across the room, that's fine. Now, why don't you try to take your polarized lens, okay, and tilt it, just like you always would, and I'll try not to lead the witness. People are getting kind of a nothing as you're turning this. I mean, it's darker, right, but it doesn't get different. Now, a moment ago, when I had you wearing the other kind of filter, when you were wearing the polarized filter, as you were turning this, you were getting darker, lighter, darker, lighter. Now you're turning exactly the same stimulus, but it isn't getting darker, lighter. And the reason for that is that the lens that you have, the filter that you have on now is not polarized, it's smoked. So we now have this uniformly diminished light coming your way, right? It's not filtered in a plane-specific way. The polarization planes are all equal. They're reduced, but they're all equally reduced in an even-Steven manner. So I think this is really cool, that you can take this one that you were wearing just a moment ago, right, the one that's one-sided. This is a smoked filter. And I could sneak up to you and put this over you, and you would say, yeah, it got darker. And I'd say, so is this one smoked or is it polarized? And you basically would have no way of knowing the answer to that question. You can't do that. But that would be a trivial distinction for many birds and lots of insects to make. They would see that right away. To give you an idea about that, if you look at my shirt and you look at Claudio's shirt, hopefully you see some salient differences right away. Right? I mean, this is, I hope, something approximately saliently white, and that's pretty saliently red. Right? And it just hits you just like that. Well, that difference would be equally obvious to a bird or an insect that's looking through this versus looking through one of the first filters that I gave you. I mean, they would just immediately see those planes of polarization as being wildly different from each other. Okay? But we're relatively blind to that physical property of this stimulus. Who's following that? Is that working? Pretty cool. And they're doing all kinds of things. They're navigating very, very long distances by looking at this. They're navigating smaller distances, but in a hurry by following the straight line because they can figure out how light is polarized up in the stars. Okay? Pretty cool. Pretty cool. Questions on any of that? Let's take a moment or two for questions on anything in part 1, part 1A or 1B. Give you another minute to take a look at your notes and make sure you're all clear on that. There's not going to be a quiz today on this, but at some point there will be an exam on all this material, right? And this would be a good moment to clarify things. And some of that stuff is familiar to you if you've had physics classes, but some of it is maybe less familiar to you if you're less familiar with the properties of light, how it can be polarized, different oscillation rates, independent of the fact that any given photon is moving at 3 times 10 to the 8 meters per second. No? Okay, we're going to do something very unusual. Many people who are in this class have an experiment to run starting in exactly 20 minutes, and we need some setup time. We need some time to get in there and make sure that we're all good to go. So I'm going to stop us 8 minutes early today, and I think I won't do this again in the semester, but today we really need to get in there, set up some things. First time we're running this. And so if you're in Psych 341, can you stay here just for a moment? We'll talk just a little bit about instructions, then I'll say go, and we'll sprint into that room and set up the computers. If you're not in Psych 341, thank you for a great session. Could you please put your stuff right back up here on your way out? I look forward to seeing you Wednesday. And remember that we have a bunch of TED Eds for Wednesday. It will be more on the human eye. Yes, please. Yeah, we didn't get to the blind spot. So hang on to that sheet. We'll do the blind spot when we come back on Wednesday. We'll start out with the blind spot demo. And if you don't bring this back on Wednesday, I'll have plenty of them for you. Okay. And if you're in Psych 341, can you please stay? We have a little bit of instruction to do before we head out and set up the experiment.
$3.67.
Oh, okay, thanks. Thank you. All right, the other. Some different types. Yeah, thank you for separating them. That helps. I'm trying to put it all back together. Okay, we'll take a quick head count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Did I miss 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, I could do a quick check to see if somebody just stepped out or... okay, we are missing Sarah. Thank you. Okay. All right, so this is what I wanted to say first. Before we get too far into the experiment, I wanted to make sure that we're all clear for what's due on Wednesday. So today's going to be our first day to do data collection. We're going to try to do both of the groups as the experimental group, right? Because we've decided to use our own data as control data. And we never really know how many we're going to get through SONA. And as of last night, I haven't checked in the last few hours, but we had 13 people coming in just a few minutes. And then we had, I think, 3 or so coming in for the second part. So we'll see, we'll run them both as experimental groups. We also can run next Monday. So we'll have another chance to get another group, and we'll see if we can advertise this. And that might work a little bit better for us, because I think that the Psych 100 students are not yet in the habit of signing up for psych experiments. This might be the first experiment for many of them, right? So they're not used to this. So we get another week, and we might get a better sample next week. But this time, at least, we get 2 shots at it, and we'll get maybe something like 13-ish and so forth. So we'll say go in just a moment. I did want to clarify one thing for us, and that is that on Wednesday, we will not be collecting data. We'll stay right with the syllabus. And on Wednesday, we want to make sure that you're turning in a draft, and this is only a draft, of your method section and your intro section, okay, for Project 1. So Project 1 overall is worth fewer points than Project 2 will be. Project 1 is a smaller project, and we're breaking even Project 1 up into these small parts, but this is worth only 40 points of the 400 for the semester. And there's a form that you can click on here, and it gives you some instructions about what kinds of things should be in a method section, what kinds of things should be in an introduction section. You've all done those before, but I'd like to make sure that people are very clear on this. What I'd like you to do for Wednesday is turn in that assignment just like you would turn in any other assignment. And could you please bring a paper copy as well to class, because we're going to have a writing workshop on Wednesday. So you'll turn one in electronically, and what I'd like you to bring on Wednesday is a small packet that has 3 things. It's got your cover page, which has your Slater box but not your name. And then underneath that, you've got your method section. It's only a draft. And you've got your introduction. Okay, we'll do intro first, method second. And then we'll circulate those, and we'll have a writing workshop. Okay, so that's what's going to be due. And then you'll get feedback from each other and also from me. And from me, it'll be worth a total of 40 points. That's what's due on Wednesday. And I wanted to make sure that everybody was clear on that, because once we start running the experiment, it'll be a little hectic in there. And I wanted to make sure we were all clear about what's due on Wednesday. Everybody good with that? What's due on Wednesday? All right. Okay, we're still 15 minutes ahead. Why don't we say go? Can I hand to one of you a stack of CogLab disks, and maybe the rest of you can start turning on computers and loading them up. Okay, so there they are. I also have in here a stack of forms for collecting the data. I have debriefing forms, I have consent forms, okay? So take over that room and make it happen, okay? All right.
Is your class in here?
Yeah, please clean up, because we're not coming back here now. I'll clean up this, okay? And I think that room is open. And you've got to go, right?
Yes.
So you're good to go.
So,
Thank you.
Let me know what I have to do for.
Okay, that's fine. Yeah, we'll have you do some data entry some other time. Okay.
I did my NIH certificate. I just have to put it on the share.
Oh, that's
so
fine.
you can see it. But
That's
I
fine.
did it.
All right, that's fine. Thanks. Yeah,
Yeah,
you can send it to me anytime. Thanks, Liz. I'll be in a couple of minutes.